Today we're on Unit 12, Lesson 5, Independent Events. We'll be covering pages 423 to 426. I'll be using 3 colored pens, and you do want to have a calculator handy for adding and dividing. And your homework pages are page 427 and 428. So before we begin these independent events, let's just keep in mind we kind of moved away from our formula of probability of A or B, and more recently we've been working with the probability of A given B. So just keep in mind that the probability of A given B is equal to the denominator is probability of B, and the numerator is the probability of A and B. So you just want to remember that. Okay, so in the previous lesson's homework, we saw how the occurrence of one event could change the probability of another event. When this happens, we say the two events are not independent of one another. When the occurrence of one event has no effect on the probability of another event happening, we say the events are independent. So exercise number 1, decide whether or not the following scenarios have independent events. So A, a person pulls a red marble out of a bag that has 5 blue and 7 red marbles and does not replace it. Then a person pulls another red marble. Is the probability of pulling the second red marble out independent of the first red marble? Well, once we pull that first red marble, which the probability of getting the first one being red would be 7 out of 12 because there's 12 marbles total, and that first red marble is not replaced, then that changes the outcome for the second red marble. Because now there's one less red marble. Now there is, for the second red, there are 6 red marbles out of now 11 marbles. So our answer is no. Are they independent? No. Once the first red marble is drawn and not replaced, the probability of drawing a second has changed from 7/12 to 6/11. Drawing that first marble has an effect on the probability of drawing a second marble, a second red marble. Our other scenario is a person flips a coin and notes that it comes up heads. Then the person rolls a standard 6-sided die and notes that it comes up as a number less than 3. Is the probability that the number came up less than 3 independent of getting a head when flipping the coin? Oh, yes. The two events are independent. The coin's outcome has no effect. Right? The coin's outcome, getting a head, has no effect on the outcome of the die. The idea of independence is one that comes fairly naturally, but it's important in order to see if there are associations amongst two events. Let's develop a tool to test independence. Well, Of course, our tool is going to end up being a formula, which I believe we'll get to on the next page. Okay, so the spinner below is spun once and its outcome is noted. Let E be the event of getting an even number. So E is even. So I think I'll just go around 2, 4, 6, and 8 are even. Let P be the event of getting a prime number. 2 is prime, 3 is prime, 5 is prime, and 7 is prime. And let L be the event of getting a number less than 5. So that would be 4, 3, 2, and 1. They are all numbers less than 5. Find the following probabilities. A, the probability of getting an even. So probability of even, well, there's 4 out of the total of 8 possible outcomes, or 1/2. The probability of getting an even given that the outcome was a prime number. Well, probability of even given prime, we know the denominator is going to be the probability of getting prime. The numerator is probability of even and prime. Prime, there's 1, 2, 3, 4. So our denominator is 4. And even and prime. So 2 is even and prime, and that is it. So 1/4. The probability of getting an even given that the outcome was a number less than 5. Probability of even given less than 5. The numerator is even and less than 5. So that would be our 4 and our 2. So that's 2. And probability of less than 5 is 4. And 2 over 4 reduces to 1/2. We want the probability of less than 5 given even. Again, our denominator is even, 4, and our numerator is less than 5 and even. Less than 5 and even is our 2 and 4. So that's 2, which is over 4, which is 1/2. E, the probability of prime given even. Denominator is even. Prime and even, that's just the number 2. That's 1. Are even and less than 5, are E and L independent events? So, well, in other words, does the probability of even given L change the probability that is just even? Is there any difference between these two? Well, probability of even given L is up here. That's our 1/2. And the probability of even is also this 1/2. So are these independent? Yes, they are. Are E and P independent events? Let's say, does the probability of even given prime is the same as probability of even? Even given prime is up here in B, that's 1/4. And probability of even, that was 1/2. So no. So here we have at the top of the next page, page 424, our formula. Two events A and B are defined to be independent of one another if the probability of A given B equals the probability of A, and likewise if the probability of B given A equals the probability of B. You have to memorize this, so please write it down. And I will always, and this is just one, there will be a second definition for independent events or another formula that you can use to show that things are independent or not independent. So we want to say independent if the probability of A given B is equal to the probability of A. So the probability of A happening given that B has already happened really has no effect on the probability of A occurring. Exercise 3. A survey of 57 sixth graders was done to determine which subject was their favorite. The results are shown in the table below, sorted by gender. So we have subjects: math, English, social studies, science, total, and then female and male. I'm going to label female for F, and male I'm going to label not female. And male would be, math would be M. English I'll label E, social studies SS, and science S. Does it appear based on the data in this table that the preference for math as a favorite subject is independent of students' gender? Okay, so if we are testing for independence, we're going to say independent if we're looking at math and gender. If the probability of math given female equals the probability of math, or the probability of female given math equals the probability of female, or here I was just using math and female gender. Well, what about or probability of math given not female, meaning male, does that equal the probability of math? Or the probability of male, meaning not female, given math, does that equal the probability of not female? So you can test any one of these four to determine whether or not they're independent. You don't have to do all four of them, just one. All right, so I'm going back to our first one. Independent if the probability of math given female, does that equal probability of math? All right, so for probability of math given female, that's going to be the probability of math and female over the probability of female. So our numbers there are, given female. So I'm looking at here, the total is 30, and math and female is 8. So is 8 30ths, or 8 over 30, does that equal probability of math is 18 out of 57. Grab a calculator, and 8 divided by 30 is 0.26 repeating. So this is, I'm going to have to go over here. 0.26 repeating, does that equal 18 divided by 57? That's approximately 0.32. No. So these are not independent. Now, if I had worked this out, I'm going to get two different fractions, but those fractions are not going to be equal. All right, probability of female given math. So the math is the denominator, which is 18, and out of those 18, how many are female? That was 8. So is 8/18 equivalent to probability of female? That's 30 over 57. 8 divided by 18 is 0.4 repeating. Does that equal 30 divided by 57? 0.53 approximately. Again, this is a no also. And the same would happen if I tried any these other two. Right? You're going to get two different fractions than what we have here, but they are not going to be equal. Okay, so B, does it appear based on the data in this table that the preference for social studies as a favorite subject is independent of student gender? So again, please, if you would, write down independent if. The probability of A given B equals the probability of A. So in this case, we're trying to look at social studies and student gender. The probability of social studies given female, does that equal the probability of social studies? Or I could go the probability of female given social studies, does that equal the probability of female? Or probability of social studies given male, whoops, male is not female, not F. Does that equal the probability of social studies? Or the probability of not female given social studies, does that equal the probability of not female? Right. So, I'm going back to my first one. Probability of social studies given female. The female, all right, let's see. There we go. Female is 30, and social studies and female is 10. So is 10 out of 30 equal to probability of social studies? I want 10 over 30. So total for social studies is 19 out of the total 57. You know that's 1/3 or 0.3 repeating. And 19 divided by 57 is 1/3. So in this case, yes, they are independent. If I take my green, probability of female given social studies. Given social studies, that's a total of 19. Of them, 10 female, so 10/19. Is that equal to probability of female? 30/57. 10 divided by 19 is this 0.526 something. And 30 divided by 57. Well, it's the same decimal. So that must, if I math frac that, that reduces. Yeah, the 10/19. So yes. And if I tested these, we will get different fractions than what we have here, but they are going to be equal. So there is a test for independence that comes from our formula for conditional probability. All right, so we have, given that the probability of A given B We know that the probability of A given B equals the probability of A and B as the numerator over the probability of B. Do the following. If A and B are independent, then rewrite this formula and solve for the probability of A and B. Okay, so we want to solve for the probability of A and B. So let's just go back to this right here, right? And we want to solve for the probability of A and B. So I would just multiply by, I want to get this by itself, so multiply by the probability of B, both sides. Okay, so now here, these divide out, so I have the probability of A and B. I'm simply writing the right-hand side first on the left-hand side. So the probability of A and B equals the probability of A given B times the probability of B. Okay. Probability of B times the probability of A given B. You can just swap those. So the probability of A and B equals the probability of A given B times the probability of B. But A and B are independent. So if A and B are independent, we are told that A and B are independent. So that means that this here, so the probability of A given B would equal the probability of A. And if we replace the probability of A given B with what it's equal to, then we get the probability of A and B is equal to the probability of A times the probability of B. So this is what we call the product test for independence. So the product test for independence. Let me do this. Independent if the probability of A and B equals the probability of A times the probability of B. So you want to memorize this, as well as what we have from above, right? In our above box there, independent if the probability of A given B equals the probability of A. So these two you want to memorize. So there's two ways of determining independence. Two events are independent if the probability of A and B is equal to the probability of A times the probability of B. Two events are independent if the probability of A given B equals the probability of A. Exercise number 4B, the probability that a person is left-handed is 12%. The probability they have brown eyes is 42%. Okay, so left-handed is 12%, brown eyes 42%. And the probability they have brown eyes and are left-handed is 2%. Is the event having brown eyes independent of being left-handed? Well, we have several ways we could test this. We could say, does the probability of left-handed given brown eyes, just use B for brown eyes, does that equal probability of left-handed? Or the probability of brown eyes given left-handed, does that equal probability of brown eyes? Or does the probability of brown eyes and left-handed equal the probability of brown eyes times probability of left-handed? So any one of these three. Left-handed given brown eyes. The denominator is brown eyes, which is 0.42. And the numerator would be left-handed and brown eyes, which is 0.2. Oh, 0.02, sorry. Does that equal probability of left-handed, which is 0.12? So 0.02 divided by 0.42 is approximately 0.05. 0.05 approximately. Does that equal 0.12? No. So these are not independent. And you don't have to do all three of these. You only need to one. I'm just saying that there's more than one way you can test independence. The probability, but I am going to show you all three. You only need to do one when you do the homework. Probability of brown eyes given left-handed. So left-handed is our denominator of 0.12. Brown eyes and left-handed is 0.02. Is that equivalent to probability of brown eyes? 0.42. 0.02 divided by 0.12 is not close to 0.42. It's about 0.16 repeating. That does not equal 0.42. No. And brown eyes and left-handed is 0.02. So does 0.02 equal brown eyes is 0.42 times left-handed 0.12. 0.42 times 0.12 is 0.04 or 0.0504. 0.0504. And there's another no. So no matter which one you chose to use to test your independence, the answer is no. The decimals are not equal. Well, the two sides of the equation are not equal to each other. Okay, so, oh boy, that's a long video. I apologize. Oof. 5. I'm almost thinking of maybe possibly skipping this page. Yeah, I'm going to skip page 425. And let's move on to page 426. Okay. Consider the data below. And before I start this, you have to memorize. So let's write at the top. Independent if. The probability of A given B equals the probability of A. Or, another way to test for independence is independent if. The probability of A and B equals the probability of A times the probability of B. Those are two ways of proving independence. And let's not forget the definition of the probability of A given B is equal to probability of B is the denominator, probability of A and B is the numerator. Right? You've got to have these memorized. Okay, so we have student indicates he or she has asthma. I'm going to use A for asthma. So again, this is page 426. That tilde A for does not have asthma. No household member smokes. So I'm going to use not S for no household member smokes and S for at least one household member smokes. All right, so you are asked to determine if the two events are randomly a randomly selected student has asthma and a randomly selected student has a household member who smokes are independent. Okay, so has asthma and household member. So, well, right there I can say, okay, so is the probability of asthma given has a household member that smokes equal to probability of asthma? Is that the case? Or is the probability of household member smokes given person has asthma equal to probability of smokes? Or is the probability of asthma and smokes equal to the probability of asthma times probability of smokes? All right, but taking it step by step here. Find the probability that a randomly selected student has a household member that smokes. So that's simply probability of S, which is 395 out of 937. And I think I'll round to 3 decimal places here. 935 or 395 divided by 937 is approximately 0.422. Find the probability that a randomly selected student has a household member who smokes given they have asthma. So probability of S given A. That's going to equal the probability of S and A over probability of A. So our denominator is A, which is 182, and our numerator is S and A, 113. It's actually 113 divided by 0.621, I'm going around, approximately. Based on the probabilities you calculated above, are these two events independent or non-independent? Explain. Okay, so since we have these two, I'm going to say they are independent if the probability of S given A equals the probability of S. Well, S given A is 0.621, and the probability S is 0.42, so no. Not independent. The probability of S given A does not equal the probability of S. That's our explanation. Find the probability that a randomly selected student has asthma. Probability of asthma, 182 out of the 937. Which is approximately 0.194. Find the probability that a randomly selected student has asthma given they have a household member that smokes. So this is probability of asthma given household member smokes. So S is our denominator, 395, and of those 395, we're looking for asthma, 113. So 113 over 395. 113 divided by 395. 0.286, so approximately 0.286. Based on the probabilities you calculated above, are these two events independent or not independent? Again, please keep writing independent if the probability of asthma given smokes equals probability of asthma. Asthma given smokes is 0.286. Does that equal 0.194? No. They are not independent. Okay, so with the homework, please just remember your ways of testing for independence, right? Independent if the probability of A given B equals the probability of A, or the probability of B given A equals the probability of B, or the probability of A and B equals the probability of A times the probability of B. And don't forget that the probability of A given B is equal to B is in the denominator and A and B is the numerator. The homework pages follow the notes pages. So I don't think you'll have a problem with that. Okay, thank you once again. I apologize for the length of this video.